The gamma camera is a more complicated system than the non-imaging devices such as dose calibrator, will counter, or thyroid uptake. We will focus on the components of the gamma camera and how they contribute to the image formation process. The reference in this presentation in the same book, Physics and Nuclear Medicine, and it covers chapter 13 of this book. The principles of nuclear medicine studies are based on the assessment of radioactivity distribution in a given organ after in vivo administration of a radiopharmaceutical to distinguish between a normal and abnormal tissue. Such assessment of radionuclide distribution inside the patient is performed by gamma camera. And this is an example of the gamma camera used in different departments. This is the GE camera with 2 head detectors, and this is the table. So these detectors are detecting radiation, not emitting radiation. Okay, and sometimes combined with the CT here for localization and attenuation correction. However, so we said the gamma camera detects the distribution of radioactivity inside the patient. This accomplished by recording the emission from radioactivity with external radiation detectors placed at different location outside the patient. The preferred emission for this application are gamma rays in the approximately energy range between 80 and 400 keV. We said that the low energy photon less than 80 or less than 50 keV are not likely to escape the body, and so this increases the dose to the body without imaging benefit. And the high energy photon above 400 keV results in poor detection efficiency. So the radiation high energy will pass through the detector without recording or without stopping by the detector. So we need the energy between these two energy, between 80 to 400 keV for gamma camera purposes. There are different gamma camera systems. The first one is a conventional planar gamma camera. A basic problem in conventional radionuclide imaging is that the images obtained are 2D projection of a 3D source distribution. So images of structure at one depth in the patient thus are obscured by superimposed image of overlying and underlying structure. This is the problem of 2D image. So one solution is to obtain tomographic imaging, or we call it 3D imaging, 3 images which equals to multiple 2D slices of a 3D object. SPECT images are capable of providing more accurate quantitation of activity at a specific location within the body. The third type is a SPECT-CT. It is multimodality or hybrid system. The purpose of CT with SPECT is for localization to give more anatomical background, and also to use for attenuation correction to correct for the activity distribution inside the body. So in this figure, this is like SPECT-CT imaging performed by the technetium sulfur colloid. Okay, so we can see here the SPECT image with the sulfur colloid. We have here the CT scan, and this is the fused image between the CT and nuclear medicine image. X-ray imaging is considered as transmission imaging, and the radiation is transmitted through the patient, and amount reaching the detector tells us about the internal structure of the patient. Gamma imaging, however, is known as emission imaging, as the radiation is administered to the patient, okay, and the amount that is emitted and detected by the detector tells us something about where the radiation is and how it is behaving inside the patient, what is the distribution of radioactivity inside the patient. So for CT and X-ray, it is transmission, and for nuclear medicine is emission from patient to detector. The main components of gamma camera detectors are collimator, first part here, then scintillation crystal. We have light guide between the scintillation and the photomultiplier tube and other electronics. We'll go quickly through component per component. In nuclear medicine imaging, the radiation from radioactive source is emitted in all directions. Hence, we need a collimator to be fitted. Okay, an imaging collimator is used to define the direction of the detected gamma rays. So this is the main function of the collimator. The function of collimator is not to eliminate the scatter. The function of collimator is to define the direction of detected gamma rays. Gamma rays are not traveling in the proper direction, are absorbed by the collimator before they reach the crystal and detector. Actually, most of the potentially useful radiation traveling toward the detector is stopped by the absorptive walls here. It's called septa between the collimator holes. So these septa is the walls of the collimator. The purpose of these walls is to absorb the scattered or the photon which is not perpendicular on the crystal. This figure shows different types of event that may be detected by gamma camera. So we see here that the photon emitted by the patient, we inject the patient with radioactivity. This radioactivity emits gamma ray, okay? The gamma ray detected in the crystal here, this is the red circle indicate location of X-ray, or sorry, gamma ray interaction with the crystal. Okay, let's go one by one. For A here, this is called valid event. It emits from the patient, go perpendicular to the crystal, pass through the collimator and registered by the detector. B here is the detector scatter event, pass through the collimator with no problem, but after detected by the crystal, has Compton scattering and scatter and detected in this region. So this one gives a blurred image here, affect the resolution of the image. C, it's object scatter event. So radiation emitted by the patient is scattered inside the patient, interact with the atom inside the patient, scatter, then detected by the detector. But the event here represents this area, why the event started from here. So here also there is like affecting, this affect or impact the spatial resolution of the camera. D represent the septa penetration because the radiation here penetrate the septa and detected by the crystal, and this gives us some kind of artifact we will talk about later. Okay. In this graph, both images show the projection profile. This is the projection profiles of 2-point sources. In the left side, we can see that the profile without using collimator, there is a very little information about the origin of the photons because of a scatter contribution. We cannot define the exact location of where the radiation is coming, the location of emitting the radiation exactly. It is wide. We say that if it is wide, we get bad resolution. We need always thin profile to get better resolution. We need thin one. So this is like, if we look at this one here on the right side, when the collimator is installed, okay, points on the image plane are uniquely identified with line space. This is virtually, it's not actually, the collimator will not absorb all the photon and accept only the one perpendicular to the crystal. But this is just to show you the effect of the collimator, that the purpose of the collimator to define the incident gamma photon on the crystal. There are different collimators type. The first one is, and the most frequent geometry, 1-to-1 ratio between the object and image is called the parallel hole collimator. This is what we use in current days. Okay, parallel hole collimator. From this parallel hole collimator, we have different collimator. We have low energy, medium energy, high energy, general purpose. All of them are parallel hole collimator. In the past, we used to have also converging collimator. Convergent collimator is high resolution, but add distortion due to different magnification depth. And it is used to image a small organ. So small organ just do magnification. So this affects the image quality. We have also pinhole for providing high resolution, small shallow organs, and mainly used for thyroid scan. And we have also diverging collimator. imaging organs larger than the field of view. This was used historically for lung imaging when the detector was small. So we need to image lung, which is bigger than the collimator. We use the divergent collimator. In this presentation, I will talk only about the parallel hole collimator, as it is the most commonly used type of collimator nowadays. The collimator most commonly consists of a leaded plate containing a large number of holes, similar to this one. So collimator is a honeycomb of lead septa with air holes. From this cross-section of the collimator, okay, we can see there's a septa here. This is the collimator. This is the septa of the collimator. This septa has L length, the diameter of the hole, and we have the thickness also of the septa. The length of the septa and the diameter of the hole, this determine the relative spatial resolution and sensitivity of the collimator, while the thickness of the septa determined by radionuclide energy. So the collimator is the limiting factor in gamma camera system performance. It typically absorbs well over 99% of all photons emitting from the patient absorbed by the collimator septa. There is always trade-off between spatial resolution and sensitivity. Okay, resolution improves with a reduction in the width of the collimator holes D, and improve with the hole length L, while the sensitivity improve with the larger D and shorter L. Just to understand this one. So for high resolution, we need to accept only the gamma ray that perpendicular to the crystal. We don't need to detect the scatter photon, or that one is not in the proper direction. So to do that, to get higher resolution, we have to reduce the diameter of the hole here. So we accept only very few photons. And we have to increase the length of septa to reduce the acceptance angle. And this one reduce the number of scatter photon enter, or not in the proper direction to enter the crystal. But if we need better sensitivity, means we need more counts, we have to make D wider to accept more counts, and we need to make this shorter, the length of the septa shorter to accept more count. Accepting more count means the resolution will be degraded. If you need to improve the resolution, the sensitivity will be degraded. That's why it is trade-off between sensitivity and resolution. Another factor affecting the collimator resolution is the distance between the source and collimator. And increasing the distance between the source and collimator degrade the resolution. You get poorer resolution. We can see here when the point source is close to the collimator, we get good profile here with acceptable full width at half maximum. While if they increase the distance from the collimator, we can see that the full width at half maximum is wider now, means we have poorer resolution. Regarding the sensitivity, the same number of count under the curve will be achieved in both cases. So the distance from the collimator is not affected the sensitivity, but affect the resolution. So if you need better resolution, you need to keep the source as close as possible to the collimator. That's why in nuclear medicine, when we image the patient, we keep the collimator very close to the patient to get the best resolution. Ideally, collimator septa should block all incident radiation. In real collimator, as we said, a fraction penetrates septa or are scattered and detected. So septal penetration and scatter increase with energy. So increasing the energy, the penetration will increase because the incident photon has enough adequate energy to penetrate the septa and also detected by the detector. Thus, collimator are designed for energy range. Different energy range. If we use different isotopes with different energy, we have to use a proper collimator to prevent the septal penetration. So if we have radioisotopes emit gamma radiation less than 160 keV, like technetium-99 emit 140 keV, we use the low energy collimator. It is all parallel hole collimator. Okay, so in parallel hole collimator, we have different type of collimator. We said we have low energy collimator, we have medium energy for radiation between 160 and 250 keV, like gallium-67. Okay, and we have collimator for high energy incident photon. Photon has energy greater than 250 keV. We use high energy collimator like iodine-131. The energy is 360 and above. So if the septa are not thick enough, then septal penetration occur. And this is referred to star artifact. So if this is iodine-123 source, iodine-131 source, and the energy of iodine-131 is about 360. If we use low energy collimator with iodine-131, we get this star artifact. When we see the star artifact, we know that this collimator is not the proper one. If we use the medium energy, you see the star artifact is reduced here, but still we have some. With high energy, still better, but still there is septa penetration, but much better than the first one here. Questions? The primary purpose of collimator in nuclear medicine is to what? Exclude scatter, reduce the count rate, improve on the intrinsic spatial resolution, and provide spatial localization, and protect the crystal. B, D, C, A, and C. It's only one answer here. C. You remember we said the collimator installed not to reduce the scatter, okay? And it is limiting factor, so it will degrade the resolution. So it define the direction of the photon incident. Here, D, spatial localization. Spatial mean from makani, and in makan. Spatial localization define the localization here of the. And so the answer is D. It defines the direction of detected gamma ray. Okay? So don't forget this. The purpose of the collimator to define the direction of the incident photon. The same meaning is to provide spatial localization. المكاني, مكان incident photon interact with the crystal of the gamma camera. Okay? Question number 2. What occurs when a low energy collimator is used to image high energy radionuclide? Low energy collimator image, for example, like what we see, iodine-131. D, D, D. Excellent. We got septal penetration. So the second part of the gamma camera is the scintillation crystal. The scintillation crystal is the gamma in the gamma camera converts gamma ray photon incident on the crystal into a number of visible light photon. So this is the function or the purpose of the crystal. Okay, convert gamma ray photon incident on the crystal into a number of visible light photon. The crystal used in gamma camera based on photomultiplier tube, as we discussed in the previous lecture, PMT, and the crystal is sodium iodide detector. And this is just a schematic cross-section of sodium iodide crystal used in gamma camera. Usually it is one slab, it's not pixelized. So it is one slab of detector and has reflector material to enhance the number of light photon produced. Okay, and also there's aluminum casing just to prevent humidity and other factor temperature to go inside and affect the crystal of the gamma camera. Typical thickness of the gamma camera used nowadays is about 9 millimeter. One important parameter of scintillation crystal related to camera performance is the thickness of the crystal used in the gamma camera. The thickness is a trade-off between two characteristics, intrinsic resolution and sensitivity. We said there is always trade-off between sensitivity and resolution. You enhance the sensitivity, you get poorer resolution, and vice versa. Increasing the thickness of detector and increase the probability of complete absorption of gamma ray, and hence the sensitivity of the gamma camera is increased. Okay, however, the probability of multiple Compton scattering also increasing in the thicker detector, and this results in poor resolution of the image of the area of interest. So thicker crystal is good for sensitivity, bad for resolution. Okay, the thinner crystal, poorer efficiency or poorer sensitivity, but better spatial resolution because the probability is less to get Compton scattering with the thin one. And also the distribution of the light photon in the thicker one is wider here. So to define the location of incident is not as easy as the one with thin. Here the distribution of light is less. Sorry, so the resolution here the location of incident can be defined here easily. Sorry. Okay, and we can see from this like plot here, this is the crystal thickness and this is the intrinsic resolution full width at half maximum. By increasing the crystal thickness, the full width at half maximum increased. Increasing the full width at half maximum mean wider profile, mean poorer resolution. This is an intrinsic sensitivity of sodium iodide crystal as function of energy for several crystal thickness. The gamma camera is nearly, as we can see here, 100% efficient for energies up approximately to 100 keV or about 140 keV for all crystal thickness. The efficiency is almost 100%. Okay, but then the efficiency is decreased at higher energy, increasing the photon energy, the incident photon energy. This decreased the efficiency, okay, of detector with the thickness of the crystal as a relation with the thickness of a crystal. We can see that's why we use the technetium 99 140 keV. So whatever the thickness of the crystal, still we get good efficiency with this kind of energy. If we use high energy, so we have to consider thicker crystal to enhance the efficiency, to stop this kind of photon with high energy. Question. In scintillation detector using sodium iodide crystal, this is multiple answers, okay? The efficiency depends on the thickness of the crystal. High energy beta particles are detected. The sodium iodide crystal is hygroscopic. A collimator is used to reduce scatter. A is correct. B, high energy beta particle are detected. We don't detect beta particle, we detect only gamma ray and gamma camera. C, sodium iodide crystal is hygroscopic. Yes, it affected by humidity. Collimator is used to reduce scatter. We said no, it is define the direction of the photon. So A and C, the correct answers. Okay, great, excellent. The next component of gamma camera is called light guide. The light guide provides light coupling between the crystal and BMT, the photomultiplier tube. Okay, and the purpose of the light guide is to improve light collection efficiency by channeling scintillation light away from the gap between the BMT. So there is a gap between BMT. The purpose of the light guide is just to guide the light photon to go to the BMT and detected not to go to the edges of this one. So enhance the collection of light photons by BMT. So this improves the uniformity of light collection as a function of position. Otherwise, there would be a large reflective and refractive losses of light between the crystal and BMT. So it's just to enhance the collection of light photon by BMT. Okay, doesn't have other roles. So the other part is photomultiplier tube. We already talked about that BMT. Just to review that, It converts light photon to electron in photocathode of the PMT. This is the purpose of the PMT. Okay, multiplies signal through interaction with the multiple diodes. So energy here, the photon, gamma photon interact with the crystal, we get the light photon interact with the photocathode of the PMT, produce electron. The electron here is multiplied by the diodes, and at the end we get the current, and this current collected by the electrical connectors outside here and go to another electronics. Okay. The conversion efficiency, quantum efficiency, it's called quantum efficiency for visible light to electron is typically 1 photoelectron per 5 visible light photons striking the photocathode. We already mentioned that we need about 5 visible light to produce 1 photoelectron in photoelectrode here. Okay, but this is not a fixed number again. Could be 6, 7 visible light to produce 1. Okay, and this I'm saying that for purpose, we'll go for that later on. A high-speed photoelectron striking the diode surface ejects several secondary electrons from it. This occurs through many additional diode images, typically 9 to 12, okay, in all, until finally shower of the electron is collected by the anode here, and we get the output signal. In gamma camera, an array of approximately 60 photomultiplier tubes cover the entire crystal. The PM tube are encased in a thin magnetic shield also to prevent change in gain caused by changes, because the gamma head is rotating around the patient and go in different direction. We don't need the magnetic field, the earth magnetic field affect the orientation of the PMT or moving the PMT, which will change the gain of PMT. So that's why it's just covered with a magnetic shield to avoid this effect. So this figure shows a rectangular gamma camera detector with cover removed just to show the photomultiplier tube mounted in the, this is a sodium iodide crystal. Question number 4, the PMT consists of photocathode and a series of diodes in evacuated glass enclosed. PMT convert what to what? The light photons into electrical signal. All A, okay, excellent, correct. Just go quickly through the electronics to have an idea what is inside the gamma camera. We have high voltage power supply, of course. We have a pre-amplifier and amplifier. We have event positioning circuitry and pulse high spectroscopy. So pre-amplifier, the amount of charge given by PMT is very small. The signal is getting out from PMT, even though a sophisticated photo detector like PMT used, we still end up with quite a small electrical signal from PMT, okay? So this needs amplification without adding high level of noise into the signal readout. The output signal of PMT cannot be fed directly into the amplifier because of the impedance. There's impedance or resistance, we call it, impedance difference between the PMT and the amplifier. So we need something in between, which is the pre-amplifier, just to be like to deliver the signal from PMT to amplifier. This is the purpose of a pre-amplifier, to magnify or to amplify the signal and to be like between the PMT and the amplifier. The next component is the amplifier. The amplifier component of a nuclear counting instrument has two major functions: to amplify the signal even further after the pre-amplifier, and to reshape pulse from a pre-amplifier to avoid pulse pile up. Pulse pile up, that means to detect the two signals together and consider it as one. So because it is not organized here. So to avoid pulse pile up at high counting rates and to improve the signal to noise ratio. Amplifier must do this function without distorting the information in the pre-amplifier signal, which is mainly the pulse amplitude should not be distorted. This is the signal from pre-amplifier, and this is the signal after rearranged by the amplifier. So we see the amplitude of the signal here is the same of the amplitude this one. This should be not distorted because it has information about the incident photon. Okay, that's another thing, should not be distorted. The rise time, the time at which the radiation event was detected. So the time here, the event detected at this time should be not distorted. The same time here, not distorted. Just the things, rearrange the pulses to prevent the pile up, and keep the time, the rise time, and keep the pulse amplitude the same. The second component in the electronics, okay, is the event positioning circuitry in the gamma camera. In general, the goal of the radiation detector is to provide an estimate of the energy and interaction position of each gamma ray incident on the detector. The position and energy estimation circuit estimate the gamma ray energy and position from set of voltage value from the BMT. We will see that now. So we define the energy of the incident photon. What is the energy? Because by defining the energy, we can define our primary photon and we can eliminate the scatter photon. And we need to also define the position where the incident photon came from the patient to just represent the information or distribution of the patient in the image. So event position circuitry, just give you the idea, the principle behind that. So the amount of light detected by particular BMT tube is inversely related to the lateral distance between the interaction, here the interaction site, and the center of the PM tube. Ideally, the relationship between signal amplitude, this one here, and the location with respect to the center of PM tube would be linear. What does it mean here? Look at this, we have two BMT and we have event detected. Here we have the gamma photon interact with the crystal in this location. So to define the location, where is the location? We use the PMT signals. So if the event here is closer to the center of this PMT, the amplitude is increased. We have what is called, we have bigger amplitude here than here. So this is the linear relationship between the lateral distance between the event and the central of PMT. If we go closer to the center, we see the amplitude is higher here. If we go farther away, we see the shorter amplitude here. So we have long amplitude, we have short amplitude according to the lateral distance of D1 and D2. So if this one is here, we can see very long amplitude here, while here is very short. Okay, so it is a relationship. And by knowing the amplitude S1 and S2, and knowing also the D here, the D is the distance between the PMT to BMT center. This is total D, D1 plus D2 equal D. So we can define D1 and D2 and define the position of interaction of the photon in the crystal. So D1, to find D1, we have to know S2 and multiply by D divided by S1 plus S2. We can define what is D1. Again, for D2, the same thing. Then we have the coordinate X, Y. We define the exact location of interaction of the photon with the crystal. This is in simple way. Real life is very complicated to define the photon. We have millions of interaction and different way, but this is the principle of detection and the position in the crystal. Okay, we look at the amplitude and we find the location of interaction because of the relationship, the linear relationship between the lateral distance between the interaction here and the center of the PMT and the amplitude of the signal coming out from the PMT. Sorry, I'm speaking more electrons just to give you an idea what's going on inside the gamma camera. So we have BMT, the output voltages generated by the BMT are fed to what's called position circuitry or position circuit, which produce the four output, X plus, X minus, X plus, X minus, Y plus, and minus. This is the coordinate of the incident event. So this give information where the scintillation will reproduce within the crystal. So this is the location coordinate of the event. Okay, then these position signals are fed to summation, called summation circuit, which adds up the 4 position x plus, x minus, and so on, to generate what's called Z signal. Okay, the Z signal is proportional to the total amount of light produced in the scintillation event in the crystal, and therefore the total energy deposited by the gamma ray, and is used for pulse high analysis. We're going to discuss this later. So this Z is proportional to the energy of the photon incident and the number of incident occur inside the crystal. This is important, the pulse high analyzer. A pulse high spectrum displays the amplitude of signals coming from PMT. So this is the signal coming from PMT. This is our photo peak. Okay, this amplitude is proportional to the energy deposited within scintillation crystal. Increasing the energy will increase the amplitude of this photo peak. For example, if we have 140 keV technetium, we'll see this photo peak on 140 keV. Okay, this is channel different than that, but we can have the keV here. We get the photo peak at 140 keV, and this is our primary photo peak. The purpose of the main function of pulse high analyzer is to remove a scattered photon originated from patient and the crystal from the resulting image to provide better spatial resolution and contrast. So the function of removing the scatter or eliminating or reducing the scatter, it is pulse high analyzer. This is the function of pulse high analyzer, to remove the scatter, not the colorimeter. Pulse high analyzer reduce the scatter or try to eliminate the scatter from the image. How the pulse high analyzer do that? By defining the window around the on the photon energy, what we need, that specific photon energy. So we are acquiring, for example, technetium-99. We said the energy of the technetium-99 is 140 keV. We need to accept only the photons, 140 keV, not only 140 keV. We give window around that. We said, okay, we accept 20% window. 20% window plus means plus 10 and minus 10. Here is the question. Colorimeter, okay, reduce the scatter photon, but this is the, actually colorimeter absorb most of the photon interact with the detector. Most of the photon, 99% of the photon emitted by the patient will be absorbed by colorimeter. The scatter, and sometimes not scatter photon absorbed by the colorimeter. That's why we cannot say it is of course reduce the scatter, but this is not the function of the scatter. It is, by the way, it is reducing the scatter. It is reduce all the photon emitted by the patient and pass it through the colorimeter. So scatter has a role, but this is not the function. When they design the colorimeter, design it just to define the direction, is kind of lens, just to define the direction of the photon and accept only the photon perpendicular to the crystal. Okay, but by the way, also reduce the number of scatter and reduce also the true events. Okay. So again, the pulse high analyzer. You're welcome. Okay, the pulse high analyzer define the window around this our photo peak 140 keV. We say, usually we define 20%. 20% mean the plus 10% and minus 10%. Okay, so we can detect 126 to 154. Any photon detected by the gamma camera and has energy from 126 to 154 will be accepted by this setting. Okay, we can reduce the window here. We can make it 15% or 10%. We get better image with better signal. Okay, but at the end we reduce the number of count detected, so we affect the sensitivity. The count density will be reduced, but the resolution will be better. We say that there's a trade-off between resolution. We reduce the window, we get better resolution, but bad sensitivity. So the typical window used in the clinical nuclear medicine is about 20%. 20%, remember, I mean 10% plus minus 10%. Okay? Here, this is an example of selecting wrong energy window. So here the patient has been injected with technetium-99 MDB for bone scan. After scanning the patient, the image show increased soft tissue, as we see here, activity, poor visualization of bone. So they look for the reason behind that. And we found that technology selected different energy, different window. Selected that we have to select the photopeak. And for technetium-99, you have to select the 140 keV photopeak, and then you define the window 20% around this peak. But this technology select the peak of cobalt-57, which is 122 keV, and take a 20% window. So what we see here is mostly scattered photon coming from this region, from Compton area, and some of the photopeak as well. So that's why it's very noisy image here. It should be corrected. The image should be repeated and acquire again with a correct window around the technetium-99 photopeak, which is 140 keV. This is it looks like the typical bone scan. This is a different patient, just to see the difference. When we define the correct window, we get the bone, while wrong window, we get noisy image. So let's go to the questioning quickly here. A pulse high analyzer window with 20% used with technetium-99 would like reject energy keV that are less than one answer here. C, A, D, A, D, 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 okay, A, D. Okay, let's go to the correct answer now. Thank you. The correct answer is C here. So remember, we said 20% mean 10% above 440 and 10% below 140. 10% of 140 is 14. 140 minus 14 is 126. So anything above it, 126 will be detected. Anything below 126 will be rejected. So the C, okay, understood? Great. Some people understand, so, okay. So we said the photopeak is 140 keV. We just set the window around the 140 keV, 20%. A plus 10%, minus 10%. The 100%, the 10% of 14 keV, 140 keV is 14 keV. So 140 keV minus 14 keV, it is 126. And so any photon from 126 to 156 will be accepted. Beyond these two energy will be rejected. So below 126, no photon will be accepted within this window, 20%. Okay? Thank you. The last component of the gamma camera is called camera shielding. The camera shielding, this one, the cap here on the detector. And the main purpose is to prevent other sources of radiation from interfering with image information. We need only the photon coming through the collimator to be detected. If we have source here, we don't need this source to be detected by the head. So this is lead shielded to accept only the photon pass through the collimator and detected by the crystal and other electronics here. Okay, this is everything about the gamma camera. Next lecture we'll go over gamma camera performance and the image quality. Any question? I just speed up a little bit just to, you know, we are running behind the time. Shall we continue, go to the next presentation? Okay.
Yes, Mr. Mahmoud. I'll proceed to the next.
Okay, lecture number 5. It's about the gamma camera imaging, performance characteristic, and image quality. In the last lecture, we talked about the gamma camera and its component, including the colorimeter, crystal, PMT, electronics. Okay. In this lecture, I will describe the major factors that determine gamma camera performance and examine the limitation that can lead to artifact in gamma camera images and their correction. The standard test of gamma camera performance also will be summarized here, just mention some of them. And the reference for this presentation is Sorensen book, chapter number 14 and 15. The performance of gamma camera system is defined by the sharpness and detail of the image. We call it also known as spatial resolution, the detector efficiency or sensitivity, its ability to measure the energy of the incident gamma photon, so energy resolution or energy discrimination, its performance at high counting rates. Okay, the counting rate it can handle by the gamma camera without significant dead time losses. In general, a gamma camera is not capable of producing perfect image of the radionuclide distribution. It still has very limitation. The first factor that affects the gamma camera performance is the spatial resolution. It is defined as the ability of the camera to distinguish between two separate objects that are close together. Nuclear medicine images have limited spatial resolution in general, if we compare it with the radiographic images like X-ray and CT scan. The sharpness of images recorded with the gamma camera is limited by several factors, including intrinsic resolution, which arises from sodium iodide detector and other electronics, and extrinsic resolution or colorimeter resolution. Measurement without colorimeter, after removing the colorimeter, and image without the colorimeter will describe best possible performance of the detector without degrading effects of the colorimeter, while extrinsic measures of spatial resolution are made under more clinically realistic condition and include the effect of the colorimeter. Why more realistic, more clinically realistic? Because we never image the patient without colorimeter, otherwise we'll get very noisy image. Will not, because the colorimeter is not there, we get random and scatter photons. Okay, but we do intrinsic resolution. We remove the colorimeter and we measure, like there is a physics test to just examine the resolution of the camera. If there's any problem with electronics, with the crystal, we can discover by doing some test to measure the intrinsic resolution without colorimeter. Then after that, we measure the spatial resolution with colorimeter in to make sure there's no problem also with the colorimeter. Start with the intrinsic spatial resolution. Intrinsic resolution is the component of spatial resolution contributed by the detector and associated electronics without colorimeter. Intrinsic resolution arises primarily from the statistical fluctuation in pulse formation. These fluctuations arise from the following condition. So the problem of intrinsic resolution is the fluctuation inside the detector. And why this fluctuation happens inside the detector? We say that because about 20 to 30 photons are produced for every keV of gamma camera. So every incident photon, every keV of the incident photon will produce about 20 to 30 light photons in the crystal. There is a statistical variation in the number of light photons produced by the absorption of a given gamma ray energy in the detector. Sometimes it produces 20, 25, 30, so it is not a fixed number. This fluctuation of the number per keV, this affect or impact the intrinsic spatial resolution. We don't have the same number every time, so it is a statistical fluctuation. Also, statistically, all light photons produced in the scintillator may not strike the photocathode in the PM tube. Some of them will be like scattered, some of them will be attenuated, whatever. So not all the light photons produced in the crystal will be detected by the PMT. So this is another source of statistical fluctuation. Secondly, As already stated, approximately 7 to 10 light photons are required to release 1 to 3 photoelectron from the photocathode of PMT. Therefore, the number of photoelectrons that one gamma ray will produce may vary from one event to another. We said about every 5 light photons produce 1 electron in the PMT. But this is not the fixed number. I used to say not the fixed number. So sometimes 6, 7, or so there is a fluctuation. How many light photons produce how many photoelectrons? So the KeV, it produces how many electrons in the PMT is different every time. So all these statistical fluctuation inside the detector's component affect the intrinsic spatial resolution. Intrinsic spatial resolution with higher gamma ray energy, intrinsic resolution improves with higher gamma ray energy and deteriorate with the lower energy. So higher gamma ray give us better intrinsic spatial resolution, okay? Because greater statistical fluctuation occur in the production of light photon by lower energy photon and vice versa. Intrinsic resolution also depends on the detector crystal thickness. We already mentioned that. Thinner is better for resolution because thicker detector result in the greater spreading of scintillation light before it reaches the PMT tube and enhance the probability to get Compton scattering, and this deteriorate the spatial resolution. Intrinsic resolution improve with narrow pulse high analyzer window setting because scatter radiation are avoided. If we reduce the window from 20% to 15% or 10%, this enhance the spatial resolution of the camera, but of course decrease the sensitivity and efficiency of the gamma camera. Most modern cameras have intrinsic resolution of about 4 millimeter for the technetium-99, okay? The second component of spatial resolution is the extrinsic resolution, which includes the effects of the collimator and used to calculate the overall system resolution. Okay, we can calculate the system resolution by taking the square root of the intrinsic resolution square plus the collimator or extrinsic resolution square. We get the total or overall system resolution. Collimator resolution is generally worse than intrinsic resolution of the camera because the effect of the collimator. Extrinsic resolution is affected by collimator design and distance from the collimator. So this is the design. If we increase the number of folds in the collimator, this will have no effect in resolution. It might increase the sensitivity, but will not, it has no role in resolution. The hole diameter, okay, D here, if we increase the hole diameter, we get poorer resolution because we accept more scatter photons. The hole length increase, we get better resolution because we decrease the acceptance angle of the photon and can be absorbed by the septa. Septa thickness increase, this gives us better resolution because also reduce the number of scatter photons detected by the detector. The distance between the source and collimator, if it is increased, this gives us poorer resolution also. We need the source to be very close to collimator to get the best possible resolution. So spatial resolution can be evaluated qualitatively or quantitatively. Qualitatively means without number, just look at this and like observing the phantom and see how its quality is the image, okay? So qualitatively, it's like visual inspection of the image obtained by using this kind of phantoms called bar phantom. It consists of 4 sets of parallel lead bar strips arranged perpendicular to each other, and this is the site holder. Okay, the width and the spacing of the strips are different in each quadrant, as we see here: 2 millimeter, 2.5, 3.5, and 3 millimeter. The phantom is exposed to radiation and the image is visually inspected. We see which quadrant we can see. We can see this one can be seen, this one can be seen, this one can be seen, and this one is difficult to be seen. Okay, so just keep monitoring this one. If anything in bad, if the line is not linear, if there's any artifact, if we start not seeing this one, we say that the image quality is degrading. We have to do kind of calibration with this one. Okay, spatial resolution is estimated from the smallest strip of spatial distinguishable on the image. There's another way to do the quantitative by taking the line source and calculate the full width at half maximum of the gamma camera. So you get the spatial resolution of the camera quantitatively by different way, but it is out of our scope now. These images were taken by placing the source of activity at different distances from the collimator to see the changes in the spatial resolution with distance. We can see when the source is about 5 centimeters from the collimator here. This is the phantom, brain phantom. You can see the resolution. If we just increase the distance from the collimator, we see how the resolution is affected. The same thing with this far phantom. Increasing the distance, you can see how the resolution is impacted by increasing the distance between the source and collimator. Let's have a question now. True or false? Spatial resolution is lower than a planar gamma imaging. High sensitivity collimator provides better image quality compared to high resolution collimator. Reconstructed resolution improves as the distance of the detector from the patient is increased. The detection sensitivity of SPECT system is less than the planar gamma imaging. True or false on it? I don't see answers there. So D is the true, you mean detection sensitive SPECT system. So just to save time, let's go just and see the answers. Okay, this is the only true in this question because spatial resolution is lower than a planar gamma image. So the spatial resolution of the SPECT mean is lower than a planar gamma imaging. It's true because the distance between the camera and the patient, okay, is farther in SPECT camera head is closer to the patient in planar gamma. So in a planar gamma imaging, the camera is very close to the patient, so we get better resolution. In SPECT, the camera is rotating around the patient and the distance is varied. So the resolution in the SPECT is poorer than in the planar image. Okay, that's why I'm saying that the SPECT is different location from the patient, different distance, so we get bad resolution. Okay, here high sensitivity collimator provide better image quality compared to high resolution. False, high resolution collimator provides improved image quality compared to high sensitivity collimator or general purpose collimator. C is reconstructed resolution improves at the distance. We already discussed this one, it's false. The detection sensitivity of SPECT system is less than the planar gamma imaging. False, because SPECT detects photons in multiple directions. As the detector rotates, however, planar imaging detects photons in one direction only. So planar takes in one direction, while with SPECT take in different direction. So the sensitivity with SPECT is better than sensitivity with the planar images. Okay? The intrinsic resolution and collimator resolution are related to the system resolution are as, which equation here? E, okay. D. E. Okay, great. Just difficult to remember these equations. So this is the equation of system resolution or overall resolution. It is square root. This is the square root here of R square intrinsic of the R square collimator. So this is the correct answer. The second factor that affects the gamma camera performance is sensitivity. It measures how many count are detected per unit of activity per unit of time. Okay, how count, like count per minute per microcurie or count per second per megabecquerel. So how many count detected per unit of activity? So we have activity, emit radiation, emit photons. How many photons detected by the gamma camera, the ratio between the photon detected by the gamma camera and the photon emitted by the activity? Could be patient or source, whatever. This figure shows, already discussed this one, the detection efficiency versus the gamma ray energy for sodium iodide detector of different thickness. We see sensitivity improve with thicker crystal and with decreasing gamma energy. Increasing high energy will degrade the sensitivity. Discussing quickly this one already discussed before. So if increasing the number of fold collimator, this will enhance the sensitivity. If we increase the hole diameter, this will enhance the sensitivity. Hole length will degrade the sensitivity. Septal thickness, also this will degrade the sensitivity. And source to collimator has no effect on the sensitivity, okay? System sensitivity need to be measured separately for each collimator. So if you have different kinds of collimator in your department, low energy, high resolution, medium energy collimator, you need to check the sensitivity for each one. Solution of the radionuclide is placed, this is the method, is placed in the 10 centimeter diameter dish and placed 10 centimeter from the front face of the collimator and image is acquired. The sensitivity is calculated by drawing a circular region of the interest around the image of the dish and integrating all the count in the region. A second image here is recorded for an equal imaging time with the source removed to provide a measure of the background. So to calculate the sensitivity, we take the count per minute of this source and subtract the background count per minute and divide it by the source activity in microcurie, okay? And they get the sensitivity, which is the count per minute per microcurie. How many count per minute will be detected each microcurie activity of our source? Question. Increasing the thickness of the scintillation detector will result in the detector okay. Increase sensitivity and enhance resolution, increase sensitivity and degrade. Remember, there is always trade-off between resolution and sensitivity. Okay, B, C, I see it, B, D. So we say that B increased sensitivity and degrade resolution. Thicker increase or degradation of resolution. Better sensitivity, lower resolution. Correct, is B. Excellent. What is the sensitivity of camera that registers a 3000 count per minute from 200 microcurie source if the background
الصوت كأنه انقطع.
the background of this one and divide it, and in this way we get the sensitivity value here, and just follow this equation. So source count per minute, which is 30,000 minus 500, and excellent 147, almost 148, 147.5. Excellent, thank you.
هل الصوت واضح للجميع؟ عفوا. أستاذ محمود ينقطع الصوت. دكتور خالد مقطوع الصوت كمان عندك؟ أيوة. أستاذ محمود.
إيه دكتور، ما هو طالع الصوت.
إيه. تمام، خلينا نسوي ريلود للمحاضرة مع أستاذ محمود. يمكن ضغطت على ميوت أستاذ محمود.
الو.
أيوة الآن طلع الصوت.
والصورة موجودة، السلايد موجود؟
الصورة موجودة، إيه energy resolution.
اوكي، صار في I don't know, maybe الانترنت connection.
الله يعطيك العافية، مو مشكلة.
Okay, we were saying that in energy resolution, like intrinsic resolution, depends largely on statistical fluctuation in the number of light photons collected from the scintillation event. Okay, so different number of light photons are produced, different number of photoelectrons are produced. This affect the intrinsic resolution and also affect the energy resolution. Energy resolution improve with increasing the gamma energy. Increasing the incident gamma energy enhance the energy resolution. This figure, so we can see from this figure, improving energy resolution means that the photopeak, or we said full width at half maximum, becomes narrower, resulting in more efficient detection of unscattered photons within the chosen energy window, like 10%, 20%, as we said before. This increased the number of valid events recorded and improved the statistical quality of the image. But if you reduce the window, you also reduce the number of count detected, and this degrades the sensitivity. Anyway, the energy resolution for the gamma camera is typically between 9% and 11% and can be calculated by taking this equation. So energy resolution is take the full width at half maximum divided on the photo peak. This is for cesium 137, sorry. So this is for the cesium. We take the full width at half maximum 555 keV divided by the photo peak 662 keV multiplied by 100. We get the energy resolution of this gamma camera or detector. Question here. Given the following energy spectrum of scintillation detector, what is the energy resolution of this detector? We have the photo peak 662, and we have the full width at half maximum 46. If someone have calculator, so can find it out. 6.9, excellent. Yeah, it's around 7%, the energy resolution. Okay, about 7%, 6.9, 7%, excellent. We go to another factor impact the quality of the image or the resolution. I'm sorry, the performance of the camera. Its performance at high count rates. In all detector system, there will be a minimum amount of time that must separate two events in order to be recorded as two separate pulses. But the problem at high counting rates, two events can be detected simultaneously by the camera and recorded as one event. This referred to as pulse pile up. So when this happens, two pulses sum together and they produce single pulse with an amplitude that is not representative of either. So we have very high count, okay? So because of the high flux of the count, the camera cannot detect all these events. It should be there is minimum time between event and another one. So if they come with a high flux, the two signals will be recorded as one signal, and this is called pulse pile up, okay? And there's amplitude defect here. Okay. The problem here is that the overlap pulse amplitude may fall outside the selected analyzer window, resulting in a lost valid event, such as losses are called dead time losses. We said we have defined window. So when two signals combine together, we get amplitude, high amplitude. Despite these are two correct or true events, it will not be recorded by the gamma camera because it will lie beyond the energy window of the gamma camera. So this will be rejected, and this will reduce the number of count detected and affect the sensitivity of the gamma camera. So this is called dead time losses. There are two models of dead time in the gamma camera, or any detector actually. There is non-parallelizable dead time, and there is a parallelizable dead time. Okay. And detector system affected by non-parallelizable dead time, events that arrive while the first event is being processed are simply ignored, with no effect on subsequent occurring events. In parallelizable detector, events arriving while the first event is being processed would not be counted, but still would introduce their own dead time. Let's explain it in this figure here. So we have incoming events to the detector. We have 4 incoming events. And this is a detector working in non-parallelizable mode, and here in parallelizable model, okay? Non-parallelizable and parallelizable. So the event comes here, the detector here detect this one, okay? Detected and recorded. This is registered and recorded. The second one comes, it's already processed. The first one is already processed. So event 2 will be recorded as well. The event 3 comes while the 2 detector is still processing the event 2. So this will be ignored, and this one will not be recorded. Number 4 will be recorded because the processing is already done. So we have a 3 recorded event while we have 4 events. So we lost 1 out of 4. Okay, in the parallelizable system, 1 is recorded, 2 comes and recorded as well in the detector. If 3 comes, the detector is still busy processing number 2. So this will be ignored, not only ignored, the 3 will introduce its own dead time, so extend the dead time. So 4 comes here, is still the detector is busy. So this will be ignored and also extend the dead time. So we see the extended dead time now because of the event coming. So this kind of parallelizable detector, it's very difficult to handle the dead time. And if there is high count rate, it will be very problem in parallelizable detector. Okay, most radiation detectors in nuclear medicine behave as parallelizable signal, as parallelizable system, including the gamma camera. So in gamma camera, we don't increase the count to the maximum. There is a maximum count that the gamma camera can handle. Beyond this count, the gamma camera, you see the count rate is going to be decreased. It's increasing until to reach to the maximum count, saturation level. Then after that, you increase the activity and see the count rate is reducing because of this process is parallelizable here. So the dead time is extended, so the camera is not responding, and you have to stop the camera until you finish all the processing and start again. Okay, so that's why there's a limitation. There's a count rate performance of the gamma camera. There's a maximum count can handle the H gamma camera. Within its specification, there's a maximum count it can handle. I ask a question about that. So when performing a daily intrinsic flood, there's every day in the morning, the technologists or physicists come and do the intrinsic flood, expose the camera to the point source. The activity of a point source of technetium-99 should be adjusted to generate measured counting rate of no greater than 25,000 count per second to prevent what? We don't need high count for what? Great, all B. And this is the correct answer, actually. Excellent, thank you. Let's move to image quality in nuclear medicine. So if we ask a question, as radiologist, or nuclear medicine physician, what is the good image for you? Is it the high spatial resolution or high contrast image or low noise image? What do you prefer? Yes, it's all, but you cannot get all of them together. So we will get a different answer. It depends on like different radiologists or nuclear medicine. So I will answer this question by saying that it all depends on the task you want to perform. So for example, estimation of myocardial wall thickness, you need high spatial resolution. You need to see the thickness of that. So you need to see anatomy of that. Detection of recurrent brain tumor, you need high contrast resolution. If you need to detect metastasis, you need high contrast and you need low noise. So it depends what kind of task you are performing. So you prefer, okay, for this particular image, I need high contrast image. I need high resolution image, depend on the task you are performing. Okay, am I right? Image quality and clarity are general terms used to refer to the degree of visibility of relevant information in the image. So many scientists work mathematically models, like they just put models to get this kind of what is called a specified image task by doing the metric, the image metric. Image metrics like contrast to noise ratio, signal to noise ratio, they are just to combine two parameters together so to find the image metric, how to improve, for example, contrast to noise, how to improve signal to noise. So the quality of nuclear medicine image is limited by several factors in general. Some of these factors relating to performance limitation of the gamma camera already have been discussed. But in the following slides, I will discuss the essential element of image quality in nuclear medicine, such as unsharpness or resolution, contrast, and noise. In general, resolution and unsharpness refer to the degree of blurring along the boundaries between different regions of the image. But in nuclear medicine, usually defined by different uptake distribution. Okay. One of the methods to measure the unsharpness is called resolving power. It's a method to measure the unsharpness here. So we use 2 point sources of the isotope to be imaged. We move the two sources toward each other, okay? This is the profile for two sources. We move the two sources toward each other and measure the separation at which the images of the 2 points cannot be distinguished. We see them as a one lesion, for example. If we have two lesions, small lesions, or we have two isotopes, we start approaching each other, like just make this one moving towards each other, and until we get one image of the two sources. The images will blur together completely at the separation approximately equal to the full width half maximum of the image of the point. To understand, I give you example here. So if the full width half maximum or spatial resolution of the camera is 7 millimeter, the images of the 2 points will be fused together completely if the separation between the 2 points is 7 millimeter or less. Okay, so if we have two lesions, the camera has a resolution of 7 millimeter, and we have two lesions separated by this 7 millimeter, we cannot see them separately. We'll see like one big lesion. So to see them separate, so we have to enhance the resolution, spatial resolution of the camera. In summary, factors affecting spatial resolution include collimator resolution, already discussed, which is affected by collimator design and distance from collimator to the patient. Intrinsic resolution due to statistical fluctuation or variation, which is photon energy dependent. Other factors include patient motion, example in respiratory, cardiac imaging, image bloods, and image display or recording system. Anyway, so here we have images of a brain phantom obtained with a phantom stationary in the left side. and with random translation and rotation in the right side during the imaging procedure. And we can see the difference in the resolution with two images. This is with motion, this is without motion. The second element of image quality is contrast. Contrast is a measure of differences in brightness, counts, or optical density in adjacent regions of the image. For example, abnormal tissue relative to the surrounding tissue, and is expressed as this one, D1, which is the lesion here, minus D2 is the background surrounding the lesion divided by the D2. Okay, this is the count density of the lesion, background over the background. It is understood from this equation that the greater the difference between the abnormal and the surrounding tissue, the better is the image contrast. Also, it can be seen that if the additional background, okay, is added through the image, contrast is reduced. Several factors affect the contrast of the image, including background, count density, size of the lesion, and also patient motion. The major factor affecting the contrast is added background. Count that are superimposed more or less uniform over the actively distribution of region of interest. Background counting rates can arise mainly from scatter radiation. Okay, the background, the source of the background in nuclear medicine, it is because there's a scatter of radiation. So we can see here the profile, the scatter tails on the point spread function. This is the point spread function for each image. This is without a scatter, this is with a scatter. We can see that the uniform scatter background, which is added to image of a primary and a scatter photon. And we can see that contrast is affected by adding more scatter photon to the region of interest here. The second factor affecting the contrast is the count density. A minimum number of counts need to be collected for reasonable contrast in the image. The higher the count in the image, the better is the contrast. So we need good sensitivity, good efficiency of the gamma camera to collect more counts. Count density depends on the amount of activity administered and the uptake in the organ of interest. So if we increase the injected dose to the patient, we get more activity and more count, but this is not a practical way to enhance the contrast, just increasing the dose to the patient for sure. Contrast is also improved with differential uptake between the area of interest and surrounding tissue. This depends on the behavior of the distribution of the radiopharmaceutical you use, how it is uptaked by the organ, different organ, and the surrounding area. Another factor affecting the contrast is the size of lesion. Image contrast to distinguish a lesion depends on its size relative to system resolution. Unless a minimum size of a lesion larger than the system resolution develops, contrast may not be sufficient to appreciate the lesion, even at higher count density. So a full contrast recovery can be obtained for lesions with a size larger than 2 to 3 times than full width at half maximum of the system resolution. So if the full width at half maximum is 7 millimeter, okay, so we need about the size of the lesion about 14 millimeter to get the full contrast of this lesion. If it is smaller, so the contrast will be reduced. The lesion size factor depends on the background activity surrounding it and whether it is cold or hot lesion. Some lesion in nuclear medicine is called cold lesion, low uptake, or high lesion, high uptake. A relatively small size hot lesion can be well contrasted against a lower background, whereas a small cold lesions may be missed against surrounding tissue of increased activity. So bigger is better, hot is better. Okay, This is a phantom. This is a thyroid phantom. Can say different regions. This is the cold regions here, and this is a hot region. This is light background. This is high background. And this phantom filled with the technetium-99, and we can see that the hot spot here, it can be seen easily. This one cold spot, it can be seen easily because it is large region, but for this one, the cold spot and the small one, it is difficult. We can see the contrast is very low here, so it is difficult to take the cold small lesion within the body. This is the purpose of this image, only just to see that. Another factor affecting the contrast is the patient motion. Patient motion during the imaging reduces the image contrast. This primarily results from the overlapping of adjacent area by the movement of different organs. It is somewhat alleviated by restraining the patient or having them in comfortable position by shortening maybe the time, or put them in the comfortable position as just keep the patient not moving during the scan. Any question about the previous slides? Go forward. Is there any relationship between the collimation and detector and the contrast? Of course, that we say that collimator reduce the number of count density in the body. So collimation reduce the contrast for sure. And the collimator affect the spatial resolution, system spatial resolution. And we said if we need the full contrast, we need to go double the spatial resolution, the system spatial resolution or collimator resolution. So collimator affect that. If we have better spatial resolution, okay, so we get better contrast, and the spatial resolution affected by the collimator, okay. Thank you. So the third element of image quality is the statistical or random noise. I think you already discussed this one in the previous lecture, just to go through that in nuclear medicine. Image noise is the degree of variation of pixel values caused by the statistical nature of radioactive decay and detection process. Even if we acquire an image, I'll give you an example here just to understand what is the problem in nuclear medicine. Even if we acquire an image of a uniform source on ideal gamma camera with perfect uniformity and efficiency of the camera, the number of count detected in all pixels of the image will not be the same. So uniform source, it should, all the pixels have the same number of count because we expose the camera to the very uniform, okay, radioisotopes, and the camera is perfect. So we should have the same number of count in each pixel, but this is not happening at all. All we have different number of counts in each pixel. In nuclear medicine, noise is a major component of image contrast that caused by a statistical variation of the background count in and around the image. The counting noise in nuclear medicine is follow the Boson noise in the statistics. There's a Gaussian and there's the Boson noise. So that the pixel noise variance is equal to the average number of background count, and the standard deviation, which is equivalent to the noise in here, is the square root of the variance or the square root of the background count. So to calculate the noise in the nuclear medicine, we take the square root of the noise, the background, we get the amount of noise. Noise is an integral part of images in nuclear medicine. You always see noise in our imaging. This impairing the detectability of lesions. The critical parameter for detectability is the contrast to noise ratio of the object in the image, which is the ratio of lesion contrast to noise contrast. To detect a lesion or other object in an image, the observer must be able to distinguish between the lesion or object and noise-generated contrast pattern in background area of the same size in the image. So the larger the contrast to noise ratio, the better is the contrast. Okay. It is reported that a lesion should have contrast to noise ratio of greater than 3 to 5 in order to be detected. The actual value depends on the object size and shape, edge sharpness, viewing distance, also observer experience, and so forth. It's not fixed number at all. Here an example by if adding the background here, so we can see the contrast is affected by using will reduce the ability to detect small contrast. Okay, see the effect of noise and the contrast. Increasing so the factor affecting the noise, increasing, we are talking about the count density now. Increasing the count density will reduce the noise level. The reduced noise, to reduce noise, increase either examination time or the administer activity. Increase the administer activity will increase the patient dose. Again, we cannot just increase the patient dose just to get better image quality. This is not following the ALARA as low as reasonable achievable. So we have limiting. So we cannot exceed some limits. We have specific dose. We cannot exceed that just to get better image or we get 4K image for the patient. We have to follow the guidelines. But we can see the difference here between the count. If we get 1,000 count and if we acquire 100 kilo count, we can see how the noise here and here much better image than this one. Another way to lower the noise level is by increasing the pixel size. Changing the matrix size from 265 to 128 pixel means we have bigger size of the pixel. For example, reduce the noise level by a factor of 2. But by increasing the size of the pixel, this will degrade and influence the spatial resolution of image. You know that the smaller pixel is better for resolution, bigger pixel size is get poorer resolution for the imaging device. Finally, image processing such as a background subtraction and digital filtering can be used to reduce the noise level and increase the contrast. We can use the filter, the low pass filter, for example, just to cut the noise and accept also all the low frequency signals. So this also enhances the noise reduction. So this is just explanation how the count density affect the noise. So when choosing matrix size, as we increase the matrix size, okay, I mean, less count will be found in each pixel and noise will be increased. Increase the matrix size mean we reduce the size of the pixel. Noise in gamma camera follow a Poisson distribution with the standard deviation of the pixel value equal to the square root of the number of counted pixel. So if we have 100 count, the standard deviation is 10. So the noise is, we take the 10 over 100, the 10 is the background, over the 100, so we have 10% noise, okay? So we have 10% if we have 100 count. If we have 10,000 count, the standard deviation is 100%. So the noise is 100, the ratio of the noise to the number, the total number of count, 100 to 10,000 is only 1%. Okay, so increasing the count density will enhance the image quality by reducing the noise. Here, the noise is 10% of the total count. Here is only 1% when they increase the count density. So if we could increase the data acquisition time, we could keep the large matrix size and still limit the noise. But there's a problem here. To double the matrix size from 256 to 512 matrix, this would take 2 to 2, it's like about 4 times longer time. So you get, this is unpractical. So if you image the patient in 20 minutes, you need more than 1 hour to finish the patient. This is not a practical solution. So there are different parameters you need to play to get the better image quality and not also increase the dose to the patient. Question. The reduction of image noise by reducing high frequency information is called, one answer here. Only one answer. We say there's another way to reduce the noise. there's to apply kind of what? Yes, correct. Filtering, like low pass filter, Gaussian filter, or whatever you have in your system. Okay, filtering. This is like this low pass filter allow for low frequency to be detected. The noise is considered high frequency. This high frequency will be cut here, not this one here. It is the low pass filter allow for low frequency and cut the high frequency, which represent the noise. So filtering can reduce the noise. Just go quickly through the quality control of the gamma camera. The performance of gamma camera need to be tested routinely to detect any change in the performance. Routine QC tests are performed daily, weekly, monthly, and also annual assessment should be performed by the qualified medical physicist just to compare the baseline acquired during the acceptance testing. So gamma camera is very sensitive, so it needs very comprehensive quality assurance program, because if from day to day it will be affected. If the temperature is high and low in the room, it affects the crystal and affect the reading. You need to do the calibration and many things. So quality assurance for the gamma camera, quality control test should be followed strictly in with the gamma camera in nuclear medicine. So these are the planar tests performed routinely and annually. Most of them are covered in this lecture and the previous lectures. In the next few slides, I'm going to discuss briefly the uniformity and resolution test. We discussed the sensitivity, we discussed the spatial resolution. I will go just through the uniformity. So interpretation, as physician, interpretation of clinical images taken with the gamma camera rely on the assumption that differences seen are due to the differences in the tracer distribution in the patient only, and not differences introduced by the system. We don't need to see any lesion because of the system artifact from the system or the crystal crack. Any changes in the distribution should reflect the distribution inside the body. So the uniformity procedure check the response of the detector to a uniform radiation is uniform within defined limits. What does it mean? So we expose the detector to uniform radiation. The response of the detector should be also uniform, because we are exposing the detector to uniform radiation. We should not see here variation in the number of count. If there's variation on the number of count, we just do calibration that taking the average count and distribute it to all pixels, and this is called uniformity correction map. So to do the uniformity, intrinsic uniformity, we take the point source, okay, and keep it 5 useful field of view, okay, distance, just to get uniform irradiation to the detector, and we measure all the uniformity value, and we have also specification. Beyond the specification, you need to consider to do kind of calibration to correct for uniformity. In addition to intrinsic uniformity, you have to do also system uniformity to check the collimator also. Extrinsic mean the collimator is N. And this is done by using the cobalt source, the uniform cobalt source. Okay, why we use cobalt source, and we put the cobalt source between the two heads, for example, and we check the uniformity. The response of the camera should be uniform because we are exposing to the uniform radiation source. Why we use cobalt 57? Because the energy of the cobalt 57 is about 122 keV, which is very close to the energy of the technetium 140 keV, what we use in the clinic. So this mimic the technetium, but has half-life greater than about 270 days. So we can keep it for 1.5 years in our department. We can use it every day to check uniformity. Here we already discussed the quadrant phantom. We check the spatial resolution by the quadrant phantom, either intrinsically without the collimator, or we can put the collimator and check the spatial resolution qualitatively. And here just the difference between the intrinsic image and extrinsic image, we do the bar phantom, check the resolution without the collimator installed and with the collimator installed. And we can see here, I don't know if you can distinguish that the resolution here is better than extrinsic because the impact of the collimator. That's everything about the image quality and performance of the gamma camera for today. Next lecture will be about the PET scanner. So if you have any question, please let me know now. If you need a break or
اي مستر محمود، لو ناخذ بريك 5 دقائق. كم ليكتشر بقى لنا؟ 2.
في 2 عنده، وفي بعدين question and answers. يعني اذا بتحبوا ببعث لهم اياها انا حاطط الكويستشن والانسر والاكسبلانيشن. They can read it by themselves and they ask me, send me email or whatever.
حلوة الكويستشن اند انسر، نخليها كمان زي ما صار مع مس مرام، نخليها في وقت الامتحان تصير لها
ممكن
وقتها.
نأجلها وقت الامتحان، نستثمر هذول الاسئله لوقت الامتحان.
صحيح.
ممكن.
تمام، اجل الحين ناخذ بريك.
اي خليها
Okay.
15 minute بليز عشان يكفي الكل.
Okay, 15
15
minutes and
minutes.
we come
إيه.
with 2 presentation and that's all for today.
عشان الصلاة برضو.
ان شاء الله.
Okay, great.
15 minutes ونرجع.
حياك.
Okay.
عفوا أستاذ محمود، تسمعون الصوت؟ أستاذ محمود ما حد يسمع.
الحين سامعين؟
ميوت الحين سامعين. ايه
ايه بس كان في مشكلة عندي.
تمام تفضل.
اوكي شايفين السلايد الحين؟
اي نعم.
Okay, let's start now. Bismillah ar-Rahman ar-Rahim. Hi, lecture number 6 about the positron emission tomography. I will cover the basic principle of PET imaging, how the data acquired in PET scanner performance, quickly about qualitative PET imaging, and the hybrid image PET-CT and some artifact. The reference again is Sorensen book, chapters number 18 and 19. PET is a sensitive, fully quantitative, non-invasive functional and molecular imaging tool enables imaging of biological process. It is diagnostic imaging techniques for choice for many diseases. It's mainly for oncology, cardiology, neurological disorders. Like it's really one of the best imaging devices can be used for such kind of diseases. So the PET and CT, if combined together, you get very high quality image because PET give very good quality of function images, and CT give attenuation correction and give also localization, add anatomical image to the PET, and give very high image quality. The problem or the drawback of PET is expensive, and also the radiopharmaceutical use with PET produced by cyclotron, and it has short half-lives. So you need cyclotron in the place or nearby to get the radioisotopes for positron emission tomography imaging. This is the two machines what we have in King Fahd Specialist Hospital. We have the old one, Philips Gemini PET-CT, and we have time of flight biograph MCT flow PET-CT. Positron emitting, the principle of imaging in PET is positron emitting tracer is injected into the body. We know that a proton-rich nuclei decay by positron emission, and emitted positron travels short distance. For F18, for example, it's less than 1 millimeter in soft tissue. The distance the positron travels before annihilating depends on positron energy and material it traversed through. Positron collide with electrons or with another atom, causing what's called annihilation. Annihilation process converts the mass of positron and electron into pure electromagnetic energy. 2 511 keV photons are produced and are emitted in opposite direction, as we discussed earlier. The mass converted to the electromagnetic radiation here. Annihilation photons are detected by opposing detectors. Energy discrimination, energy window, similar to one in the SPECT camera, is used to ensure that each gamma is 511 keV. There is another window in PET, in addition to the energy window, is called coincidence time window. It is used to ensure that gamma ray or photon emitted by the annihilation comes from the same annihilation, hence ensuring accurate localization of the tracer. So let's explain that one. So we have proton-rich radionuclide decay by emitting positron. Positron combine with electron and form what is called positronium, the proton and electron. The positron and electron, which they rapidly annihilate, and they produce two photons, each one with 511 keV opposite each other. The angle between them approximately 180 degrees. These two photons will be detected by the opposing detectors in the PET, and this event is increasing by increasing the injected dose to the patient, like positron emitter inside the patient. These some radionuclides used with PET are produced by mainly in cyclotron carbon 11 to F18, and one is rubidium 82. We take it by the generator, and you look here as you see the half-life is short. It's similar if we compare it with the, for example, gamma camera radionuclide used in the SPECT camera, like technetium 99. We talk about 6 hours. Iodine 131, 8 days, while here the maximum is 110. Is for the F18, it's almost 2 hours for F18. That's all. And all of this is example of PET radio tracer, like carbon 11 labeled with another one. Like the most common one is F18 with FDG or DOPA, FLT. This is what we use mainly in nuclear medicine, F18 with FDG. The annihilation photons, this one here, 2 photons, are detected in a ring detector surrounding the patients. So if both photons escape the patient body and are detected in a pair detector within coincidence time window, it's almost simultaneously, you can say, an event is recorded. Otherwise, the event will be rejected. So these two singles, these 2 photons, should be arrived to the detector almost at the same time, within the timing window defined by the PET system. The line drawn between the 2 detectors is known as the line of response, or LOR. Okay, this is the event, and this is 2 photon, and this line connected the 2 detectors is called the line of response. There is annihilation coincident detection in PET, which is not available in SPECT. In ACD, each of the 2 annihilation, 1 and 2, photon is known as single. This single and this is single. And the total count rate for the individual annihilation photon is called the singles count rate, the number of count detected by the PET ring or PET detectors. A coincident event is registered when 2 crystal, 1 and 2 here, detect an annihilation photons or single within a coincidence timing window, which is equivalent to 5 to 10 nanosecond. So the output signal from this coincident circuit only when 2 input receive simultaneously within the same coincident timing window less than 10 nanosecond. There's 2 types of data acquisition in PET, 2D acquisition mode and 3D acquisition mode. Data acquisition with SPECT in place is referred to as 2D mode. Data acquisition without any interplane SPECT is referred to as 3D mode. This is similar to SPECT somehow. We have collimator here just to reduce the number of photons coming from different direction. So SPECT employed with 2D, this gives low efficiency because most of the count will be absorbed by the SPECT. We need high dose to compensate for that, to increase the count density. It is lengthy scan time because we have low count. We increase the time just to get more count. Fewer count, again, it is low count rate. But the advantage, we have lower scatter photon detected by this kind of detector or geometry. In the 3D acquisition mode, we have no SPECT. We have high efficiency, more count detected. We have lower dose required because we have enough count, and higher count per dose, higher count rate, and shorter scan for sure. But the problem here, we have higher scatter because we don't have SPECT, so we need to correct scatter in this mode. So this is just to explain the 2D acquisition, okay, and okay, with the collimator, how it absorbed the scatter phantom, or this is the phantom coming with different in a proper direction, and this is the 3D acquisition. In the market right now, we don't have 2D. All the geometry, all the PET is the 3D geometry. It is installed without collimator or without SPECT. So this is what we have in the market right now. The SPECT is not available anymore in the images system available in the market. One of the strengths of PET is its capability to quantify physiological process in vivo. A quantitative error can arise due to random coincidence events or photon scatter within the body, photon attenuation within the body, or detector dead time. So we'll go by one by one now. This is the true that we have event here and get two singles or two photons detected simultaneously in the opposite detector, two opposite to each other detectors. So both annihilation photons are detected without any interaction with the patient. So this is considered as truths. The second type is a scatter photon or a scatter coincidence event. So this is the event here happen. We have one single here, one photon. The other one is scattered. So we got here the wrong line of response. So one or both photons scattered before reaching detector. Line of response represent misplaced position information. So the camera thinks that the event happened somewhere in this line, but actually the event is happened here, occur in this place. So this misplaced of the line of response. The last one is a random coincidence. Events from different decades, here two events we have here, interact with the crystal within time and window. So one photon detected here and one photon detected here within the time and coincidence time. So these two photons detected simultaneously, but they came from different events and registered as in one event. So the line of response is drawn in this area, and this is also misplaced, okay, for the typical or the correct line of response should be one here, and where here we get only one here, and this is the misplaced by the two events here by random coincidence because two photons detected within the timing window or simultaneously. And here is more explanation if you want to read by yourself what is the truth coincidence, no interaction, arrive together. Here the scatter one is scattered, okay, and we get wrong line of response. And here this is the random one, two events, and we get the two photons detected simultaneously, and we get also misplaced line of response. Attenuated photons in the gamma camera, in the PET like scanner, very little can be done to reduce attenuation. If the photon is attenuated in the body before arrive to the detector, because photons are absorbed within the body, do not reach the detector, so we cannot correct that. So we cannot play with a system parameter to correct for attenuation or attenuated photons. Yeah, scatter photon is coming here. The scatter photon can potentially be rejected by the detection system if their energy falls outside the predetermined acceptance range. The same thing, you remember the window defined in SPECT. Here, the same thing, there's energy window defined. And here it is, we have to define around 511 keV. Anything beyond like, and the window is smaller here, like narrower, we detect mainly the 511 keV photons. Anything beyond this energy will be rejected by the PET. This reduces the scatter, okay, by the energy window. Thank you. Random events decreasing by the coincident timing window. By decreasing the coincident timing window, decreases the number of the random events. So by decreasing the timing window, we decrease the number of random events. So scintillation crystal used in PET, either PGO, LSO, GSO, is used to capture the annihilation photons. Okay, same principle. Photomultiplier tube, we have again photomultiplier tube to amplify the light signal generated by the crystal and convert it to electronic signal. Same principle. 511 kV interact with scintillator, it produce optical photon or light photon. This light photon interact with the photomultiplier tube and get the electrical signal. Detection or coincident circuitry to assure that the photon which caused the signal is actually an annihilation photon. In addition to that one, similar to the SPECT, we have circuitry here, the coincidence circuitry, to make sure that this photon detected by the crystal had another one simultaneously detected. So if the two photons detected simultaneously, this photon will be accepted and registered. Otherwise, if there is no other photon detected simultaneously or within the timing window, this photon will be rejected. This is the role of the coincidence circuitry connected to the PM tube. Scintillation crystal used in PET. Desirable characteristics include high stopping power for 511 keV, means most annihilation photons are detected rather than passing through, contributing this to better sensitivity. Because 511 keV has very high energy, we need a crystal that can stop this kind of photon with high energy. So we need high density crystal. We need also good energy resolution, help project scatter event based on energy discrimination. This reduce the scatter. Okay, we need to have very high energy resolution, very good one. Short scintillation light decay time to reduce dead time and random coincidence. And we need high light output, which provide better statistics when detecting the light from signals. There are different crystal material used in PET scanner. The first one is bismuth germanate, BGO. It has very good absorption, high stopping power for 511 keV, and it is inexpensive. The problem with BGO, it's slow decay. That's why it cannot be used with time of flight new system of PET or a new technology of PET system. LSO and LYSO is the same principle. LSO created or manufactured by Siemens, LYSO by GE and Philips and other company, but they have the same everything. It has good stopping power and fast decay time, and it is used for time on flight because of its fast decay time. This characteristic is very good. This is one of the best crystals so far produced for PET scanner. GSO, gadolinium, it has good energy resolution, but lags in the other characteristics, so it is not used in current scanner. So these some characteristics of different types of PET scintillation are in the following. So density, we need high density, and we need high Z to enhance the efficiency in stopping the 511 keV. We need short decay time to process each pulse individually at high counting rate and to reduce the number of random coincident events, as we said before. Light output, we need high light output, helps to achieve good spatial resolution with a high ratio of number of a crystal to a number of photo detector and attain good energy resolution by having this one. And for sure, we need good energy resolution to reduce scatter. And we can see here that the LSO, what is like considered for most of the time of flight PET system, has very good decay time. It's very fast. That's why they use it for time of flight. And it has good density and good also Z. Okay, the light output is acceptable. The sodium iodide is much better, but this one is acceptable if compared with other detector here. And also energy resolution is good. Less number means better because we are talking full width at half maximum. Less number means narrower spectrum or narrower profile. That means better resolution or energy resolution. This is the block detector used in PET. The block detector commonly used in clinical PET scanner looks like this one. There is a crystal, piece of crystal, could be LSO, BGO, is cut into an array. You can see this one, the cut inside the crystal of a smaller element that are read out of for single. This cut to enhance the localization within the crystal. This cut just to define where the event is happening. This enhance the resolution and the localization, the PET. The cuts here, okay, in the material are filled with the reflective material that, along with the depth of the cut, the separation between each cut, this helps control the distribution of scintillation light reaching the BMT by reducing and controlling optical crosstalk between scintillator elements. We don't need a crosstalk between that one. If the event detected by this cut should remain in this cut, and because there's a reflector and there's a space, we don't need the crosstalk between the light of the light between the two, between the arrays of the crystal. And this is the typical block detector used in the PET. We have a crystal here, and we have 4 PMT read one block of a crystal. Question. This is multiple answers, okay? The property of scintillator in PET includes maximum efficiency in stopping the 511 kV, short decay time, good intrinsic energy resolution, and also high light output. Good. So I see here A, B, all A. Okay. So all of them are correct, actually. Thank you for your answer, but it's all of them, because as we said, we need high stopping power for 511 kV. We need short decay. Okay. The desire is to process each pulse individually at high counting rate. To reduce the number of random coincidents, we need very high decay detector. And also C was good intrinsic energy resolution. Yes, we need good energy to discriminate energy. And here, highlight output, yes, it helps to achieve good spatial resolution. Okay, all of them are correct. Regarding positron emission tomography, detector sensitivity is a major design. This is multiple answer again. Detector sensitivity is a major design consideration in PET. Bismuth germanate, BGO, crystal have greater intrinsic efficiency for higher energy photon. PET resolution is greater than CT. Positron emitters are produced in cyclotron. Okay, D. So, okay, great. So for sure, PET resolution is not greater than CT. CD resolution is much better than PET resolution. That's why we bought CT with a PET to enhance the anatomical information of the PET image. Otherwise, all of them are true. So detector sensitivity is a major design consideration. PET, yes. The BGO crystal have greater intrinsic efficiency for high energy photon, yes. The positron emitters are produced in cyclotron, yes, like O15 and F18. Okay. Scanner performance. Important performance characteristic of PET system includes sensitivity, the same thing, spatial resolution, energy resolution. In addition to that, we have here temporal resolution. It is related to time resolution. We have also count rate capability. The number of count can be handled by the scanner. Correction for dead time and scatter fraction and other parameters. Baseline performance can be assessed through objective measure of this during the acceptance testing when we receive the PET scanner or any imaging device. So we have to do acceptance testing just to measure all these parameters and compare it with the specification of the machine and make our baseline. So every year we measure these parameters and compare it with the acceptance test values and see if it is degraded. The performance of the scanner can be evaluated, and if there's any correction required, will be corrected. The first factor affecting the spatial resolution is the depth of interaction. The trend in modern scanner system has been to decrease the width of individual detectors and to increase the total number of detector elements surrounding the patient. And this will enhance the resolution by reducing the size of the detector. The problem can occur when photons are incident, like here, incident on one detector, but penetrates through to an adjacent detector. So detected in this one here. Can you see the mouse here on the screen? Okay, good, thank you. So photons are incident in one detector here, but penetrate through to an adjacent detector and here, and the line of response is misplaced and drawn in this area. So this area is called positioning error or misplaced error, because it should be detected, the line of response should be this one here. But because the penetration of the photon from one detector to another, we get this one here. And this is called the depth of interaction problem in the PET. Okay, so it gives rise to loss of resolution at more peripheral location. Especially here, it's difficult to get the depth of interaction. The problem in the peripheral location, you got this effect that affect the spatial resolution and peripheral area. Second factor involving the physics of positron is that annihilation photon almost never are emitted at exactly 180-degree directions from each other. This positron, when it reaches the end, you remember we said the positron means the electron and annihilate each other, and the mass of positron and electron converted to the 2 photon energy with 511 keV. And this 2 photon will be ejected or will be emitted in 180 degree, so opposite to each other. But this is not the real things, because it will not be exactly 180 degree. There is here a specific angle, very like small angle, deviated from 180 degree, and this is called the non-collinearity effect. Okay, and this is due to small residual momentum of the positron when it reaches the end of its range, because the positron will mean the electron still has some energy, some momentum, and electron still has momentum. It's not zero. To get 180 degree here between in the annihilation, the positron should be zero. The speed of the positron should be zero, steady, and meet the electron, and also has no momentum, so we'll get 180 degree opposite direction, like 2 photons with opposite direction with 180 degree. But this is not the scenario. Positron has always momentum. That's why we never get exactly 180 degree. It should be little bit less than 180 degree. And this causes blur image. This is like blurring the image, and they affect the spatial resolution of PET. By increasing the diameter of the PET, this non-collinearity effect increase. Like if we increase it from, for example, from 60 to 80 centimeters, the approximately 2 millimeter will be affected of, like, will be degraded for the full width at half maximum, or for the spatial resolution. So the non-collinearity affects the spatial resolution of the bit, and this is inherently mean that we cannot change it, because this is the behavior of positron emitting by the radioisotope we use for imaging. Another factor affects the spatial resolution, the positron range. So we know this is the positron here. Okay, this is the atom eject a positron. This is rich, proton-rich atom, okay, or nucleus. Emit positron. The positron move, and it has range, then annihilate in this region. So to get accurate registration or acquisition, the annihilation should come here. The event should be detected in this area, but the positron move a specific distance, specific range, then annihilate here. This distance degrades the spatial resolution. If the positron has higher energy, will move also farther. If it is low energy, it will move a little bit less. So anyway, the positron range affect also the spatial resolution of the image acquired in PET. This is just to show the positron range here from different radionuclide. You can read it and see just compare the positron range in water and And these things, you just can read it and just follow how the range and how the range is related to energy also. Sensitivity of PET scanner is another parameter of the image performance. Sensitivity is determined by the geometry of the detector arrangement in the ring, the absorption efficiency of the detector themselves, or we can say the stopping power of detector material that can stop the 511 kV and absorb that phantoms. Sorry, absorb these photons. A small ring diameter increases sensitivity, and if we have a smaller ring diameter, the advantage that decrease the effect of non-collinearity. We said increasing the diameter of PET will affect the effect of the non-collinearity. Also, this small ring increase the depth of interaction, increase the effect of random and scatter. This is the small ring. Let's talk about the new technology of PET, which is called time of flight. We know that PET detects line of response, like here. However, the location of the actual annihilation will be somewhere along its entire length, somewhere here. We don't know exactly where the event, okay? So if the field of view at the center is 70 centimeter, the diameter of the ring here, then this annihilation event could have occurred anywhere along the path. If we could actually determine the exact location of the coincidence event, then resolution and the signal to noise ratio would be improved. So here what is happening in the time of flight. This is the conventional bit. So this is the event could have happen or occur in anywhere along this line of response. While with the time of flight, we can define the approximate location where the event is occurred, like in this area, not here, not here. This is the line of response, but I know the event occur in this location here. So how this happened? Time of flight bit is based on the assessment of difference of the arrival time of 511 kV annihilation photon, T1 and T2. Okay, traveling at speed of light. So we know the speed of this photon, speed of light. So we have the speed and we have the time, the arrival time of each photon. So if we have the speed and we have the time, this arrives within 3 nanoseconds, this arrives within 2 nanoseconds. So we know this is closer to this one than this one. And we have the speed of light, so the system can estimate the location of annihilation by knowing the arrival time and the speed of the photon. It can estimate the location of the annihilation event. So this is the conventional, as we said, without time of flight. With time of flight, because this arrived faster, so we can estimate that the location of annihilation is closer to this side. And by knowing the speed of light and the time, we can estimate more accurately the location of the coincidence event. Okay, that's why we need fast scintillation crystal, and that's why we prefer LSO and LYSO, because they have very fast decay detector, and we don't like PGO because it is very slow detector. PGO is very good, efficient detector. It has very good stopping power, but it is very slow detector, cannot be used with time of flight. Most of the bit system in the market now is time of flight because this is enhanced resolution, enhanced contrast to noise ratio. It's a great bit system. Another concept or parameter I need to talk about, it's standardized uptake value, SUV. It is very famous quantitative value in bit. We say that PET is a quantitative imaging process, and one of the important advantages is its ability to measure absolute regional radiotracer concentration within the organ. Okay, however, the value will depend on the amount of activity injected, length of time from injection, and also patient size affect this quantitative issue. So semi-quantitative measures were introduced to overcome this. The most commonly used semi-quantitative parameter is called standardized uptake value, or SUV. SUV is defined as the tissue concentration of a tracer, okay, divided by the injected dose multiplied by the normalized patient weight. So this is the way to calculate the SUV. These factors affect the SUV. Many factors can affect the reliability. So duration of uptake period. After inject the patient in PET, for PET imaging, the patient wait for almost 1 hour, then go for imaging. So increase in SUV with increasing time, okay, in malignant lesion are injected. So if this time increased than 1 hour, so the SUV will be different. So you need to standardize the time after injection. So especially for follow-up scans. So if the patient waits for 1 hour for the first scan, he has to wait another, same thing, 1 hour. Otherwise, the SUV value will be affected. Partial volume effect is already explained in the previous lecture. This underestimation of SUV in lesion with diameter that are smaller than 2 to 3 times the spatial resolution of the scanner. You have to adopt optimal partial volume correction factor installed in the machine to correct for partial volume effect. This gives underestimation of SUV. Size of the region of interest and non-uniformity of the tracer distribution in the lesion. This low SUV gives you the low SUV heterogeneity inside the tumor, okay, for the large region of interest and high random error in the smaller region of interest. You need to standardize also the region of interest selected. Attenuation correction and reconstruction method also affect the SUV, and this underestimation of SUV with highly smooth reconstruction. Also, you need to standardize the protocol, acquisition protocol, and the processing protocol. In general, the major challenges to quantitative PET can be categorized in 5 classes. The first one is called instrumentation and measurement factor. And these factors that relate to imaging system performance, and that acquisition protocol included spatial resolution, random scanning time. It's all under instrumentation and measurement factors. The second category is called physical factors. Those related to the physics of photon itself and photon interaction. Okay, like attenuation, scatter photon is all related to the physical factor. Reconstruction factor like filtering, system modeling, this is all for reconstruction parameters. We have also category of physiological factor related to patient motion and other physiological tissue, respiratory motion, PET imaging transmission scan, misregistration between PET and CT, tracer or kinetic, and so on. Methodological factor issues related to difficulties in developing accurate tracer kinetic model, especially at the voxel level. So these all that limitation for the quantitative PET imaging. Let's go quickly about the hybrid image PET and CT system. PET typically provide very little. Sorry, do you have any question before we proceed? Okay, so PET typically provides very little anatomical information. We say this is functional imaging. Relating radionuclide uptake to high resolution anatomic image, CT or MR, it greatly aids localization. So the purpose of hybrid imaging with the functional imaging, it is good for localization and also used for attenuation correction. Okay. We can see the advances in PET and advances in CT here. So we have a new detector material in PET like LSO and LYSO. We have new reconstruction method. We have a better spatial resolution and also improved image statistical quality. In CT, we have a spiral scanning, we have multi-detector technology, and we have also extended field of view, especially for radiotherapy patient for treatment planning. This is very useful for them. PET-CT has now been rapidly accepted by the medical community, and the standalone PET system are no longer being in the market. So you will not find, rarely you will find PET alone without CT. PET is a combination with a CT machine for localization, as we said, and for attenuation correction. So this is just an example of PET image and a fused image between the PET and CT. The current status of PET-CT technology. Also, the PET and CT detectors remain separate subsystem. Many software function of modern PET-CT system run on common platforms. So we have one acquisition and also sometimes one processing workstation, and they are working under the common platforms. The PET-CT system have incorporated with 4, 16, 64, and now even higher number of slides of CT to get better image quality, and can be also work as a backup of CT imaging device. The CT component of PET can be used for the other things, like you can get the diagnostic. If it, better to have diagnostic imaging in the CT than come to have PET-CT again, so you can get diagnostic image and of CT, and you get PET fused to that, so you save the number of images patient will go and save the radiation dose. The main advantage of CT-based attenuation correction is that speed with the data can be acquired. Previously, the attenuation correction can be acquired by moving the germanium source around the patient to get the attenuation correction. Now, with a few seconds, the CT can do that. Whole body PET-CT scan can be done in a few minutes, mostly related to PET component. Patient motion continue to be a problem because the PET takes longer time. So any motion of the patient will affect the image quality. PET-CT acquisition protocol for standard F18 FDG. It gives you just a scenario how the patient accepted, admitted in the nuclear medicine department, and goes step by step. So patient pre-arrival preparation, complete fasting for a minimum of 6 to 4 hours before the scan, and include cessation of a tube feeds, intravenous fluid, candy, even breathements. Everything should be stopped before the scan. Consumption of plain water is permitted. Avoid exercising for 24 hours or 48 hours to decrease muscle uptake. Effect of elevated blood glucose. This is because we know the FDG, okay, preferred blood glucose should less than 200 milligram per deciliter. F18 FDG and glucose compete for glucose transport and also for phosphorylation by hexokinase. You know that things better than me. I'm just giving the protocol. So the end point here that a glucose competing with FDG, so the distribution of FDG will be affected if the glucose level in the patient is high. So the uptake will not go, the organ will be, for example, a little bit saturated, so the uptake if in the lesion will be affected by the volume or the quantity of the glucose inside the body. In the clinic, patient is injected with 10 to 15 millicurie, depends on the size or weight of the patient, and also the type of machine. If you have time of flight machine, even 6 millicurie is enough for imaging. Patient rests quietly in uptake room for about 1 hour. The patient should be comfortably warm to avoid brown fat uptake. Shortly before end of 1 hour uptake, patient uses restroom to void the bladder. Before patient lies down in the scanner table, they remove all metallic objects that could cause CT artifact. Then CT localization scan performed or scout image. Then the CT scan, the body area to be imaged. Then PET scan is performed immediately after the CT scan. So let's take it in here step by step. We have, first of all, we take the survey or scout image. Then we get the CT of the area we want to scan. After that, we do the CT reconstruction. We go for PET, about 10 to 20 minutes acquisition. We get the PET image, apply the scatter correction and attenuation correction from the CT image to PET image. After that, we do the PET reconstruction, then a fusion between the CT reconstructed image and with PET reconstructed image, and we get the final image here between CT and PET. There are several challenges that face the use of dual modality imaging. First of all, higher absorbed dose to the patient, inherent difference between CT and PET in image matrix size, and also resolution in CT much better than PET. You need to find a way just to overcome this one, to compose or to fuse the two images, CT and PET. Also in the CT, we use the X-ray beam with 30 and 140 keV, while the energy transmitted by the patient is 511 keV. To apply the attenuation correction of this one to this one, we need to do kind of a transformation, linear transformation, to get the accurate attenuation correction map for a 511 keV from the 30 to 140 keV of the X-ray used in the CT scan. So this is just kind of artifact can be found in the PET CT. So we can see here, this is the first one, misregistration between CT and PET image resulting from respiratory motion. So we can see region decreased uptake is demonstrated here, okay, in the diaphragmic region. You can see the vertical row here, and this is called cold artifact. And this is because of the motion of the respiratory, you can get this kind of artifact. This is uncorrected images. The attenuation map is not applied to this one. So it is less, we cannot see that big artifact here. Another one is the truncation artifact or discrepancy between field of view in the PET and CT. So if portion of the patient, as we can see here, while they are outside of the CT field of view, this causes high attenuation at the margin of the CT image, leading to PET activity overcorrection in this region and actively underestimation of outside region. Okay. So the solution is reconstruct PET and CT image to the same field of view, 70 centimeter, using interpolation resolve this artifact, as you can see in this image. This is the same image after correction, and after we consider the field of view of PET and CT is same, 70 centimeter, we do interpolation, and this can correct the truncation artifact. Artifact due to metallic implants, as you can see here. The presence of metal in the body, such as artificial hip joint, can cause streak. We know that in the CT. And this can then contribute to attenuation correction error in PET image. So you have lesion here in PET, just to make sure this lesion is not like because of disease or because of metastasis or whatever, you look at the non-attenuated correction images in the PET, and in that image, the attenuation correction is not applied from CT, so you will not see this lesion for metal artifact. So that's how you can see that it is related to the metal artifact or it is real lesion inside the body. I'll go for a question quickly here before end of the lecture. So please correctly match difference between positron emission tomography and single photon emission tomography to SPECT. So the difference between PET and SPECT. So let's go one by one. PET, it involves annihilation coincidence detection. Yes, here it involves gamma ray detection. So this is the difference. This is correct. It uses technetium-99, this uses F18. This is wrong, yeah? This is not, because F18 used with PET, technetium used with SPECT. A tracer have a long half-life, tracer have short half-life. This is also false because short half-life for PET isotopes, long half-life is used for SPECT. Okay, the energy of annihilation photons is higher than the photon energy of radionuclide to SPECT. Yes, here is 511 keV. It provides higher sensitivity in detection of emitted event. Here, through PET detects 2 gamma ray for each decay to trace the line that finds where the emission of gamma camera, thus sensitivity in PET is higher than PET. So in PET, we have 2 coincidence photon detected in the event. For SPECT, we have 1 single photon detected per event. So the sensitivity of PET always better than the sensitivity of SPECT. Question. The similarity between SPECT and PET include both are based on a tracer principle. Okay. The radioactive emissions are recorded by the sensitive radiation detector surrounding the patient. The recorded emission from the integral representing the accumulated activity along lines passing through the subject. The last one, both are transmission imaging. So let's see the answer here. So all of them are true except the last one, SPECT and PET emission imaging. So both are transmission imaging. Yes, what to do? Are emissions. Yes, it's not a transmission. We say it is for CT and X-ray. Both are, it's emission imaging, not transmission imaging. Okay. The next one will be like simple presentation about radiation protection in medicine. We just go through it quickly just to see how to consider like radiation safety in nuclear medicine. Okay, please let me know if you have any questions. Sorry, it was very fast just because we are running behind the time. So if you have any question, please let me know before we proceed to another one. Okay, shall we proceed to? Okay, let's finish this. Okay. Time of flight, I closed the presentation. Time of flight is just different than conventional PET scan, that in time of flight, we can define the location where the event, we say there's a coincidence event. We have area, the lesion collect the, from this lesion, the uptake of FAT, for example, we have FDG accumulated inside the lesion, inside the body. This lesion emit positron. This positron, from that location, we have annihilation coincidence that 2 photons will be produced and detected by the gamma camera, sorry, by the PET scanner, 2 detectors in the PET scanner, okay? The location of annihilation, we don't know in the conventional. It is, we have line of response, and this event could be anywhere along this line of response. In the time of flight, we can define the exact, not exact, approximate location of the coincident event between the 2 detectors by calculating the time, arrival time of each photon, and we have the speed of light of each photon. So we have the speed and we have the time, so we can calculate. It's not easy like calculate speed. There is a mechanism to calculate the arrival time of the photon to the detector. And by knowing the arrival time and knowing that the speed of flight of this photon, the machine can calculate the can localize the coincident event between the 2 detectors along the line of response. Okay. Thank you very much. Okay, this is the last presentation for today, radiation protection in nuclear medicine. We'll go through quickly the types of radiation sources, basis for radiation protection in principle, then radiation protection and nuclear medicine in general. We have two types of radiation sources, either it's going to be external source or internal source. So external source means the radioactive source outside the body and you expose to the source from outside your body. Internal source, that either the source enter your body either in ingestion, inhalation, or it could be contaminated in your skin, and this contaminated enter your body, so you are contaminated from inside. Example, iodine-131 is volatile and can be inhaled by, if you don't have good ventilation, so iodine-131 can go through you through the inhalation. So the basis of radiation protection in general is justification, optimization, and dose limitation. Justification means a particular use of radiation cannot be justified unless there is a net benefit arising from that use. And also there is no alternative cannot be used, non-ionizing radiation like ultrasound or MRI. And always benefit should be more than the risk if you want to proceed and go for ionizing radiation. Optimization means that all exposure are to be kept as low as reasonable achievable. This is like famous principle of ALARA called as low as reasonable achievable. ALARA principle can be applied by educating and training of the people using the radioisotopes or radiation in general, design consideration, shielding calculation, operation and radiation protection programs should be implemented in the place. The last one is dose limitation. The dose received by individual resulting from all practices should not be exceed the recommended limit by the international and national regulations. And this is the latest one for effective dose for radiation worker, like people working with radiation in radiology and nuclear medicine, it is 20 millisievert per year, okay? And it's during the 5 years, divided by 5 years, and should not exceed 50 millisievert per year. Okay, so take it easily, 20 millisievert per year, it is the maximum limit for radiation worker. Length of eye, 20 millisievert for a radiation worker, it is 15 millisievert for public, and one for effective dose for public is 1 millisievert, while the radiation worker 20 millisievert. The skin, 500 millisievert for incubation worker, 50 millisievert for public. For the extremities, hands and feet, 500 millisievert for incubation. Should not have anything because the public should not work with radiation. So just go by, this is the radiation base, we say justification. If the test is justified, we proceed. If not, we consider another thing. So we ask ourselves, will it benefit to the patient? So if yes, we proceed and go for optimization. If not, we choose non-X-ray procedure. Optimization means have I choosing and followed the correct examination to produce optimum result. So if yes, we proceed and we consider the limitation. If not, we review the techniques. Okay, if limitation are staff protected and patient dose low, yes, we can proceed. Otherwise, we need to initiate the quality assurance program. So what is the dose limit of the patient? Do we have dose limit for the patient? Can you answer this one? Do you know what is the dose limit for the patient? How much the maximum we can give to the patient? Okay, great. So there's no dose limit to the patient, yes. There's no dose limit. It depends, like as you said, it depends on the prescribed dose the test is going to do. But always you have to apply the three bases: justification, optimization. Justification that should be justified, the benefit more than the risk, and optimization give as low as reasonable achievable. Don't keep just injecting the patient radioisotope just to see better image quality. We say the count density can be increased by increasing the injected dose. But this one, increase the dose to the patient without any justification. Okay, thank you. Radiation protection principle, this is famous. We have to decrease time next to the radioisotope or radiation source, we need to increase the distance from the source, and also we need to increase the amount of shielding or use the proper shielding. Reducing the time around the radiation source reduce your exposure for sure. And this is really a linear relationship between the dose and time. Reducing the time will reduce the dose. Okay. The distance radiation dose decrease at the square of the distance from the source. And this is very famous relationship. It's called inverse square law. So if one double the distance from the source of radiation, the exposure rate is reduced not to 1/2, it will be reduced to 1/4 its initial value. This is because it is equation, the inverse square law. Scatter radiation is the most common type of exposure you will receive in diagnostic radiology. It's reduced to 1/1000 the exposure the patient is receiving if you stand only 1 meter from the patient. Okay, so consider the distance is very important in addition to the time. Shielding, the purpose of radiation shielding is to protect individual working with or near radioactive source or X-ray machine. So we can use personal shielding by wearing the apron with 0.5 millimeter in X-ray, but this is not very effective for higher energy, because shielding the lead apron with 0.5 millimeter is effective with X-ray about 75 kVb. If we have, for example, 100 kVb, if we use a potential energy or potential voltage, 100 kVb, we get protected 75%, okay, effective by 75%. In nuclear medicine, 140 kV, it's only absorb maybe 50% or less than that. So, and for nuclear medicine, we have to consider thicker apron. We cannot consider the same apron every time. So nuclear medicine is not very effective. So in people in nuclear medicine, you don't see them wearing apron because it is not very effective. So they apply the distance and time better than shielding in nuclear medicine. We have to also use the proper material for shielding. So for alpha particles, sheet of paper is enough to stop alpha particle because it is heavy material and interaction is very high. So alpha particle can stop by paper. So we don't have any problem with like internal radiation of alpha. So if alpha particle is on the surface of your body, on the skin, it will not enter inside your body. It will burn or interact with the surface of the body. The range of alpha particle is very low. Low energy and high energy beta can be used. Plastic or perspex with lead can stop the beta particle. Gamma ray and X-ray can be stopped by lead or concrete mainly. Neutron can be reduced, or we can get thermal neutron by applying water, or also concrete, and water is the best shielding for a neutron. Question here quickly. The regulatory dose limit millisievert per year to a member of the public is what? A, B, C, D, E. What is the limit for the public? C, okay. You know, C. We say that, okay, thank you. So the correct answer is C. The limit dose for the public is 1 millisievert per year. For the radiation worker, usually radiologists consider as radiation worker here in Saudi Arabia. So it's 20 millisievert for radiation worker. For population or for public people, it's only 1 millisievert per year. The maximum dose public can get it. The scatter radiation intensity at 1 meter in diagnostic examination expressed as percentage of the patient's skin dose is most likely how much percentage? The scatter radiation intensity at 1 meter. Okay. C. Okay, I have C and D. So let's explain that. The answer is C here, 0.1. So the scatter intensity is likely 0.1%. We said, you remember in the like in previous slides, we said if you just increase 1 meter from the patient, you get 1/1000 scatter, like amount of scatter. 1/1000, it is the same like 0.1% of what the patient get. 1 meter from fluoroscopy patient, the radiologist is exposed to, for example, 0.02. Send the patient receive about 20 milligrams per minute. So you see how much you save like radiation, or to protect yourself if you just keep 1 meter from the fluoro patient. If a radiologist were to increase the distance to a fluoroscopy patient from 1 meter to 2 meters, his or her radiation dose would likely be what? Half of the dose of 1/3, 1/4, 1/5, or 1/8. Okay, great. All straight C I have here means everybody understand the inverse square law here. Okay, and we can see after, you can see here that increase 2R means 1/4, you get double that, you get 1/9, double that, you get 1/16, and so on. So radiation protection necromedicine, we have some problem that we are dealing with open source. We cannot switch on off the open source. It's always emitting. Liquid radioactive material poses both an external and internal radiation hazard. Radioactive patient and radioactive waste can both lead to radiation exposure to member of public, because after injecting the patient with radioactivity, the patient himself or herself is a radioactive source. Moving in the hospital, moving between people, this like also expose other to radiation. A pregnant patient and staff and member of the public need special consideration to protect the fetus from radiation. Patient and staff who are breastfeeding need special consideration to protect the child from any radioactive material that may be in the milk, because this kind of radioactives will go to the milk and the baby drink it and also exposed to internal radiation hazard. Higher energy radiation makes shielding more difficult. Staff protection, as we said, we have internal and external. So internal by ingested or inhaled radionuclide, external from the vial, syringe they use, from the patient themselves. So the good practice is to wear protective clothing, apron if necessary, use surgical rubber gloves just to prevent contamination. This will not protect you from radiation, but from contamination, not to come to your skin. Work behind the lead L block barrier like this one. Place activity to designate the place after use. Use long forceps to move the vials containing radioactivity. Work under fume hood while handling radioiodine because it is volatile. Checks for contamination after an operation and wash your hands. Eating, drinking, chewing anything inside the laboratory hot lab, it's prohibited. Wear personal monitoring badge, TLD or other, okay, just to make sure that you are to measure the dose after a while adjusting the volume in the syringe, preparing the dose or removing the air bubble. The tip of the needle must be within the vial and not in the open, otherwise you're going to contaminate the area you are working in. Observe the concept of distance and time when shielding is not possible. In handling radioactive patient, work behind bed shields. So as we said, use shield made of lead or tungsten and with lead glass to protect yourself. 3 millimeter thick shield reduce the exposure by the factor of 1,000 if you just put the vial inside this lead shield. Keep in mind the inverse square law in reducing the exposure to fingers. When you handle the syringe, you put your finger just as far as possible from the radioactivity in the syringe. Okay, finger position on a syringe is an important factor in reducing the exposure to hands. We can see here that this is the vial containing 10 gigabecquerel of technetium-99. If we have 2 millimeter of lead, the dose behind its lead, it's about 1 milligram per hour. while without shield it's 560 milligram per hour. You see the difference if you handle it from here or you handle it from here. Again, also your finger position in the syringe with no shield or with shielded. With no shield, you can see here, this is, you can get about 20, if we have 400 megabecquerel of the technetium, if you hold the syringe, if you just put your finger in this area, you get about 20 millisievert per hour. If you just go farther away from this activity, you get only 0.4 millisievert if you just consider the distance. With shield, it's farther also better. You can get nothing almost if you have shield and you just keep your finger away from the activity. So always consider to have shielding the syringe and also consider where your finger when you inject the patient with the activity. Here again, also the annual dose to the finger, mainly coming from the injection of the patient. Okay, so you just consider to use the shield for syringe and keep the distance from the activity, you get less dose. Here, different more like scan and how much activity, typical activity for each, we have 900 megabecquerel for bone scan. So if you just stand 30 centimeter from the patient of bone scan, you get 24 millisievert per hour. If you just increase that to 100 centimeter, you get only 5 millisievert per hour. And you can compare for other tests as well. Patient protection. Okay, this is typical effective radiation dose from nuclear medicine examination for the patient. For the brain, for example, you get 14 millisievert. For bone technetium NDB, you get 6.3. Okay. The protection for patient, avoid unnecessary examination or treatment. You need to be, the exam should be justified. Unnecessary exposure optimization, as low as reasonable, achievable. Inadequate examination, which can lead to incorrect or incomplete diagnosis, should not be done. So you cannot also reduce the dose to the minimum. So after that, you said, okay, I need to repeat this scan because the image is not clear. So you have to consider the optimization. Give adequate dose, but not too much. Also, misadministration, you give wrong radioisotopes, or you give extravasation or whatever. Misadministration also increase the dose to the patient with no benefit. The protection of pregnant patient, administration of radionuclide for diagnostic or radiotherapeutic procedure to women pregnant or likely to be pregnant must be avoided unless there are strong clinical indication. Also, if you are breastfeeding, please notify the staff. This should be clear in the department because some patient doesn't know that also the breast milk affected by the radioisotopes taken in the nuclear medicine. Consideration for women who consideration for women who are breastfeeding, many radiopharmaceuticals are secreted in breast milk. Consideration should be given to postponing the procedure. If a procedure is performed, the child should not be breastfed until radiopharmaceutical is no longer secreted in the breast milk. Advisory note should be posted and clear for the patient. And here is the recommendation for how long they should feeding interruption time. For most of the technetium, there is no recommendation, okay, 4 hours or something like this. For iodine 131, for example, it should stop the breastfeeding. It cannot be given after that. So if you get the iodine 131, so feeding should be interrupted forever. I mean for this baby, not forever. Sorry. The protection of the public, go quickly here. Dose limit, we said it's 1 millisievert per year. Okay, we need to safe storage, transport, and disposal of radioactive material to protect the public. We need adequate shielding design in the facility, especially in the waiting room. Entry is restricted to control and supervised area, imaging area, or area where they're injecting in the hot lab. So it should be restricted for the public people. Radiation emergency and accident If there is a contamination, you have to follow the contamination process by evacuate it, notify the radiation officer, use the decontamination kit, place the absorbent in the sheet, especially. So you just read that, follow the procedure, how to handle the contamination inside the department. Is go step by step. If there is skin surface, if your skin is contaminated, most important, don't panic. Okay, remove with contaminant with absorber paper and then wash hands or the surface in the hot sink several times with soap. While washing hands, take precaution that the water does not splash on any other part of the body. Also measure the radiation level after repeated wash by the survey meter. We say the Geiger meter is the best one to measure the contamination because it is sensitive. If the radiation level is still high, use strong detergent and wash hand repeatedly. And of course, you have to notify the RSO in a duty just to give you advice. Eye, the same thing. Don't panic. Remove the contaminant with absorbent paper or the eye in a thin covering other part of face. You don't want to distribute the activity here and there. So repeat the procedure several times and measure the radiation level and also notify the radiation safety officer in the facility. If the radiation source is lost, to prevent this to happen, keep the inventory of radioactive source. The source are locked and any movement is known by the inventory folder. In case of loss of radioactive source, the RSO first check for possibility of misplacement. Otherwise, the CO should be informed, and also the radiation safety officer and sometimes the police, because this is considered the radioactive source loss or theft. It should be the regulatory should be informed. So this is the end of this lecture. Sorry, it was very fast. My voice cannot be like for several hours talking. It's very difficult to cover nuclear medicine, physics, and radiation protection in one day. So I try to do my best to give you most of the information.
صراحة ما
يعطيك العافية أستاذ محمود.
معنا.
الله يعافيكم إن شاء الله.
لا صراحة اليوم يعني يوم نيوكلير ميديسن بامتياز، وإن شاء الله أرجو أن الكل وصلتهم يعني الأساسيات حقت النيوكلير ميديسن، وكمان تطرقت لأشياء كمان يعني كارنتلي الحين قاعدة يعني موجودة، وإن شاء الله بإذن الله كل التوفيق للجميع، وألف شكر أستاذ محمود.
حياكم الله وسامحونا على القصور، إن شاء الله تكون وصلت المعلومات وإن شاء الله الله يحفظكم.
أكيد إن شاء الله.
يعطيك العافية.
الله يعافيكم. راح ابعث لكم سوفت كوبي برزنتيشن، واي سؤال ايميلي موجود بالبرزنتيشن، اي وقت انا ممكن اتفاعل معكم. حياكم الله. شكرا.
تسلم، اهلا وسهلا، الله يعطيك العافية.
شكرا.
نشوفكم يا جماعة بكرة على نفس الموعد.
بإذن الله. الله يسلمك.